today's lesson is applications of the normal distribution. I just want to let you know the z-scores and all this normal distribution is quite important because, as you can see, it's used in a quality control and predicting outcomes. It's pretty important for business-wise, okay? Let's have a look at the example 18. So a company produces a kilograms packets of sugar. A quality control check found that the weight of the packets was normally distributed with a mean weight of 0.995 kilograms and standard deviation 0.03 kilograms. The company policy is to reject any packet with a weight outside 2 standard deviations from the mean. Okay, that sounds all right. Now, part 1. What is the smallest weight allowed by the company? First, we have to collect all the information that we need. So the mean is 0.995 kilograms, and the standard deviation is 0.03 kilograms. Okay, and there's a special condition applied, isn't it? The company, anything that weights outside the 2 standard deviations, which is here and here. Oops. Here. So anything here and then here, that will be thrown out because it's not good enough as a quality control. So if we want to find out what is the smallest weight that it's going to be accepted, we could have a look at second standard deviations, which is the mu minus 2 sigma will be the minimum you can take in. Okay, so you could actually sketch the bell curve standard deviation and then work it out from the mu, but also you can just simply calculate if you want. So 0.935 kilogram is the smallest weight the company will accept. Next one, what is the largest weight allowed? You could take that as mu plus 2 sigma, isn't it? So that's, or you could just use the bell curve. Now, if I use this, it'll be 0.995 plus 2 times 0.03. Put that in your calculator. It's 1.055 kilograms. That's the largest one we're going to get. And if it's more than that, they'll throw it away. Next question: what percentage of packets will be rejected? Okay, so we're just looking at the empirical rule here. So we are accepting 2 standard deviations up to that, whether below or above. And then after that, it's rejected. Okay, so we are accepting all of the 95% of the product, okay, packets. It's good quality. But after that, it's not. So that just means 100% take away 95% will give us the whatever its percentage it's going to be rejected. So it's going to be 5%. Now just have a look at all the wording here, okay? Especially, that's not a problem. I think you can just write that down as the company rejects 5% of the packets of sugar. That's okay. But if you don't draw the bell curve, if you need to explain it, okay, why, this is sort of recommended how you're going to write it. So about 95% of weights lie within 2 standard deviations. Just to, keep that in the wording, what they use, lie in the within, how many standard deviations of the mean, and then so 5% will lie outside this area, something like that. What percentage of large packets will be rejected? So it's quite obvious, if you picture it, 5% is altogether is rejected. But it's a symmetrical. So the lower part is a half of 5%. The upper part is a half of 5%. So therefore, 2.5% of the upper part is rejected. Okay, so let's have a look at the wording here. Since the normal distribution is a symmetrical, the 5% is made up of 2.5% of larger and 2.5% of smaller packets. Therefore, the company rejects 2.5% of the larger packets. Okay, so you don't have to be exactly like this. Here, I think it's important you mention normal distribution and symmetrical. And therefore, it's half of 5% is on the lower part, 2.5% the upper part, therefore 2.5 of the larger packets, something like that. Part B, the mean shelf life of a spice is 13.4 weeks and the standard deviation is 1.8 weeks. Would a shelf life of 20 weeks be unusual? Why? I mean, it's obvious it would be unusual. That's why they're asking you why. I would actually draw the normal distribution bell curve. So that's 13.4. 1, 2, 3. 1, 2, 3. Okay, so the next one is a 15.2, and the next one is a 17. The next one is 18.8. Okay, now you can see it is a special, unusual, I mean, isn't it? Because that's our 3 standard deviations above the mean. Okay, and 20 weeks, it's like right there somewhere. That's like 20 weeks. So it's in the part of 0.15%. And then it goes to all the way to 8. Okay, so that's 20 weeks is outside of that 99.7% already. Therefore, it's unusual. Okay, so how are we going to write that? This is just the example what the textbook says. So it says that the shelf life of a spices almost certainly lies between 8 and 18.8 weeks. Most of it is here. Okay, just normal basic stuff. But this one is 20 weeks is outside of this range, you know, the range which is 8 to 18.8. So it will be unusual. Find the z-score of a shelf life of 15.5 weeks. So now we have to use the formula, don't we? Because it's asking you to find the z-score, raw score, mean, standard deviation. Z-score, we don't know. Raw score is 15.5. And standard deviation was 13.4. No, that's a mean. Standard deviation was 1.8. Okay, so let's put that in. 15.5 take away 13.4 all over 1.8. Put that in your calculator, 1.17. Okay, so that's your z-score of your raw marks or weeks of 15.5. The third one, okay, what percentage of shelf lives would be expected to be between 13.4 and 15.5 weeks? Now, you could use just a normal distribution bell curve or the z-score one, standard normal distribution. Okay, so I've got both here. Now, I suppose you could use both, but let me give you a bit of a questions about that. So we are looking at between 13.4, 15.5. Okay, it's here. Also, this can be in a z-score, can be written as like that, because that's what we've been dealing with from the question. Okay, so we've been dealing with 13.4 and 15.5, so we can use that. So that's this one here. Okay, Either way would be okay, but when we're looking for area under the curve, I wonder how we can do that for this one. Because the z-score one, we have special power, which is the probability table. Remember the z-score tables? So we can use that for the z-score. But with this one, the first one, from between 13.4 to 15.5, I'm not sure how we can calculate this. Let's have a look at if we use the z-score. Let's have a look. So we got this in between, so we need to separate it into two. So one will be, so what I'm doing is I'm taking that, take away all the way the other part from the here. Okay, so from here, area for all up to here, take away this part. Okay, from 0 to all the way to the negative. So let's see. So I'm going to go Z 1.17, take away. That's what will give us the area in the middle. Okay. So now this is 1.17 is a z-score. Okay, it's not the area, it's a z-score. So that means when we go to the table, I'm just going to put the table here, right here. So it's 1.17. So I'm going down to here 1.1. I'll just go up to here 1.1, and then I will go to 0.07, which that will give me 1.17. Okay, and then my area is this. Okay, so I'll just rewrite this here. And this is 0.8790, and when it's a 0, it's the 0.5. Middle part, the area of the middle part is 0.379. Okay, now we want to change that to percentage. Why? Because the question said what percentage of the shelf lives would be expected to be between 13.4 and 15.5. So we want to convert this area to percentage. So times by 100. So that will give me 37.9%. So how do we write this in a wording? 37.9% of shelf lives would be expected to be between 13.4 and 15.5 weeks. Now, that's not too bad, isn't it? Because you're just rewriting the question, just with putting the correct answer. That's all. Example 19. Now, this one is the what it says here, using the z-scores and then compare two data sets. Okay, so let's have a look. So we are comparing two people. In year 7 at a school, the mean weight of students was 59.4 kilograms and the standard deviation was 3.8 kilograms. So that's year 7. In year 8, the mean was 63.5 kilograms and the standard deviation was 1.7 kilograms. John in year 7 and Deng in year 8 both weighed 68 kilograms. I see. Which student was heavier in relation to his here? Just by looking at it, I reckon, I don't know, what about you? It seems like John might be heavy because they're both the same weight, and John's year 7, so I'm just assuming he might be heavier.
Maybe it'd be Deng because their standard deviation is bigger. I mean smaller for year 8.
Deng that is a very, very good observation there, because what I've done was I just looked at the weight kilograms, right? Whereas was it Antonina spoke?
Yeah.
Yeah. So what she saw was standard deviation. So for year 7, standard deviation was 3.8 kilograms. So that's a bit wider. Whereas year 8 is 1.7. That's just small. So that's what Antonina reckons is the dang. You might be correct, Antonina. Okay, let's have a look. So, of course, it's comparing something to different things. Is Z scores. That's Z score does the best. Okay, so John is year 7. Year 7. Dang is year 8. And they're both are 68 kilograms. And John's min is 59.4. And the standard deviation is 3.8. That's quite big. Okay, so that means for Deng is 63. The mean I'm talking about, 63.5, and the 1.74 standard deviation. Okay, all right. So 68 is our raw marks or raw scores or weight. So let's have a look at the Z score for John. Z equals raw mark was 68, take away 59.4 is the mean, and 3.8. So that will give me 2.263. 2.263 standard deviations above the mean. Okay, what about Deng? Z equals 68 take away 63.5 divided by 1.7. That gives me 2.647. Aha! There you go. Antonina was correct. So 2.647 standard deviations above the mean. So therefore, the Deng weighted more in relation to his year group than John. Okay. Well, that's all for today's lesson. Quite short one. Well done.